Welcome back, Earth Science, to another chapter. This one is on weathering, soil, and erosion. So now that we've talked about, up until this point in class, we've kind of talked about how the Earth builds itself through volcanoes and earthquakes and mountain building. And now we're going to talk about how we take these processes of weathering, soil, and erosion and wear down these large mountains and these large structures. So to begin, weathering is the breakup of rock due to exposure at the surface of Earth. So this is happening all the way up at the very top of the crust. There's two types of weathering. There's mechanical weathering and there's chemical weathering. And in mechanical weathering, we are physically breaking apart rock into smaller pieces. We also call this physical weathering or disintegration. The composition of this rock is not changed. So on this big rock slab here that has been split into many, many smaller rock slabs, this is still the same type. If this was a big chunk of granite, all of these little types are still granite. Nothing has changed chemically about this piece of rock. Some kind of forces for mechanical weathering are things like ice is a very good mechanical weatherer. When water freezes, it expands. This is why you don't leave your can of soda or your water bottle inside of the freezer, because that water will expand and could potentially break it, create a mess. So this water inside of these cracks is creating more pressure, causes these rocks to crack further, and this is a process called frost wedging, because then this wedge here will continue to work its way down and continue to push until it eventually breaks the rock into two chunks. Another thing about water and mechanical weathering is this process of wetting and drying. As this substance, whatever it is, this shale, this rock that contains clay, as it's wet, this clay will absorb the water and it's going to swell up, get much bigger, take up much more space. And then when it shrinks, it dries up. As it dries up, it creates these really big cracks, which then creates this nice spot for rain to go inside, for wind to pick up particles, and create some more mechanical weathering at the surface there. Abrasion is another type of mechanical weathering where we're taking water, wind, or ice, and it is moving rock, it is moving sand, it's moving pebbles. And as these pebbles, rocks, things move, they are abrading or scraping onto other things. So water can tumble sand, pebbles, and boulders just the same way as like a rock tumbler or an ammunition tumbler, if you've ever seen one of those, where it's going through that cycle of just like continually spinning and the things are clacking against each other. This is like what a tumbler does. This abrasion is what's creating those very smooth rocks and river. Wind can blow sand and very small pebbles across a rocky plain. And glaciers can pick up really, really big chunks of rock and carry them over great distances. And glaciers are coming up. They get their own chapter. They are an exciting kind of formation, so we'll get to them eventually. But the definition for abrasion is any mechanical weathering where rocks, sand, or pebbles are grinding against one another. All of the sand on the beach is a product of abrasion. These very big chunks of rock here, as they're getting dragged along this glacier before it melted here, they are doing a lot of abrading. There's lots of smaller bits in here that you can see that have been scraped and ground down and twisted into these much smaller pieces. Plants and animals are going to actively weather rocks in this mechanical process. Things like mosses and other small plants are pushing their roots, they're pushing themselves into these cracks. As this happens, larger and larger plants start to fill that space. As soil starts to accumulate, as these mosses start to die and leave behind their nutrients. And eventually, this is enough soil for burrowing animals to come in. They create holes that allow more air and more water to reach the bedrock. This causes the bedrock to weather further, which allows for more plants and more animals, and the cycle continues until you have some really rich and fertile soil. Upward expansion, or this process of exfoliation, this is as these rocks are being pushed upward. They are from below, usually from tectonic or igneous, like plutonic things underneath them, like magma. As they're getting pushed up, they become exposed and they're able to for weathering to start happening to them. Granite is something that is very typical to be buried underneath a lot of stuff, and as it gets exposed, uh, as the sediments are eroded away, this creates lots of cracks as this granite is popping out of this kind of ground here or being pushed upward slowly. This expansion creates a lot of force, causes that granite to crack. We can also get these really cool exfoliation domes. This one's in Yosemite National Park, but these are these round domes made of granite that happen when this granite is pushed upward and exposed. Now all of this surface area is able to be weathered on. Luckily, granite is a pretty hard on the most hardness scale, so it weathers fairly slowly. The second type of weathering is chemical weathering, which occurs almost everywhere. And when I say almost everywhere, I mean anywhere there's water or water vapor. All of your chemical weathering is going to involve water. It can also include the addition of acids and oxygen, but water has to be present in some capacity. So water, and when we split rocks with water, we call it hydrolysis. And hydrolysis translates to literally water cutting. So we're using water to cut a substance. We'll have water that will react with other substances. Common substances that are weathered by water and through this chemical process, are feldspars, hornblends, augites. They will dissolve in water and they'll form our clay minerals like kaolinite. So water also has the ability to form acids, and this acid has the ability to dissolve a lot more things than just water could by itself. And a common acid that's formed this way is carbonic acid. And carbonic acid is formed when carbon dioxide dissolves in rainwater. We get lots of more carbon dioxide from productions of factories and from automobile exhaust. So we see an uptick in acid rain in areas that have those. When this rainwater seeps into the ground, it's going to more aggressively react with feldspars, hornblends, augites, and our biotite mica to weather this rock away. One of the substances that carbonic acid really likes to weather is calcite. It dissolves pretty much entirely when it's exposed to this water with carbonic acid. This creates very large, hollowed out underground caverns. This weathering is occurring down here, but that does have its own risks associated with it. Carbonic acid can also form acid rain when water reacts with that carbon dioxide, but water can also react with sulfur dioxide or nitrogen compounds to create acid rain. And acid rain is not great for plant life. As you can see, these trees here have lost all their leaves. They're not looking very healthy in this area of acid rain. But they can also cause structures made of concrete, stone, and metal to wear out more quickly, affect wildlife, and negatively, all kinds of negative effects from acid rain. Oxygen is able to help chemical weather, and whenever it does, we call it oxidation. It is very efficient at weathering substances with iron in them, things like magnetite, pyrite, biotite. And whenever we have oxidation forming, we get these rusts or rust oxides that are forming. So the rate at which something weathers is determined for using a series of factors. It's not just one factor. Under normal conditions, weathering is a fairly slow process that takes a long time. But some factors that affect it are the surface exposure, the composition of rock, and the climate at which you can find that substance inside of. So for surface exposure, a good rule of thumb is the more surface exposure of rock, the faster it will weather. So on this rock here, which is being broken apart, each time we get more and more surface area as this water, as this ice, as this air is able to get into more and more of this rock, it will split, and then we have double the surface area of what we started. And this weathering will continue to happen faster and faster and faster. The composition of rocks is important for weathering. Different rocks are weathered at very different rates. Quartz is almost impervious to chemical weathering, and it has very few cleavage areas, so mechanical weathering doesn't really break it down very quickly. But compared to biotite, which is affected by both mechanical and chemical weathering, it is weathered very quickly. It is weathered down incredibly quickly. Sedimentary cement, when we talked about sedimentary rocks, we talked about them being cemented. The composition of cement affects the rate at which they weather. Calcite cement weathers very fast, where silica cement is more resistant and weathers much slower. Climate is our third thing that affects this kind of rate of weathering. In warmer and wetter climates, we have both mechanical and chemical weathering in the form of rain for mechanical, and chemical weathering is this water getting in there and forming these different compounds. So igneous and metamorphic rocks weather very quickly in climates that are warm and wet. In colder, drier climates, things like frost wedging and mechanical weathering plays a much larger role. There's not as much chemical weathering in these areas. So we're not dissolving rocks, we're breaking them down into smaller pieces. All right, so with weathering, we get soil. Since the beginning of time, Earth's rocks and surface has been fighting against this process of weathering. Weathering has led to these valuable deposits of mineral as these rocks get broken down. And this provides materials for sedimentary rocks, and it also creates the very important substance we call soil. And soil is a collection of loose, weathered rock and usually organic material mixed in there as well. So let's talk about how soil forms. So soil forms from what we call a parent material. Depending on the type of parent material, we categorize them as two different types. There is residual soil and transported soil. In residual soil, this is the type of soil where the parent material is in the bedrock beneath the soil. So down here, and as these bits of bedrock break up, they migrate up, they become smaller and smaller. And usually soil of farmland or really fertile, we think of fertile, nice, rich soil, is this type. The second type is transported soil, where the parent rock is transported before it's deposited. It can be left by winds, rivers, or in this image over here, glaciers. We can also have this very fine soil that's left over from floods. And the parent material is loose soil, boulders, sands, and gravel. The important part about this material is it's not from the area. It is from a different bedrock. It has been transported to this area. So this soil will look very different than the bedrock underneath of it. So as this soil forms, it forms as its parent rock is weathered away, whether this is transported soil or soil that is actually from that area. The climate and the type of weathering that is making this play a large part. As these rock chunks are broken down, we have decaying plant and animal remains that are mixed with these materials to form this nice, rich soil. For soils that are old and really, really healthy and nice, we think of nice farmland, fertile soils. We call these mature soils because they usually take a long time to form. When we study soils, we can kind of look at them as we dig down through them. Looking at this cross section and looking at this nice kind of chunk here, this is a thing called a soil profile. In mature soils, so soils that have a long time to form, we'll get three distinct zones called soil horizons. And they are the A, the B, and the C horizons. In the A horizon, we call this one the topsoil. This is generally gray or black in color. Darker than soil in other regions of these soil profiles because it contains humus. Humus is the organic material that forms from decaying plant and animal materials, and it has all these nice nutrients that new plants love and flourish off of. In the B horizon, we call this the subsoil. This is usually a reddish or brownish color, and it's from these iron oxides that have washed down from the A level here. They've come down into here, creating that nice red color. Probably should have used a different color to do that. Nice red color there. It also has any clay or very fine silt that has washed down from the A horizon. And we also find calcium and magnesium in these levels. And these plants here are growing down their roots to collect this nice calcium and magnesium. In the C horizon, we are down deeper now, and it's made of these slightly weathered parent materials. We got some rocks in there. We've got some bigger chunks in there. This is directly above the bedrock. So directly underneath this level is the bedrock. This is the lowest level that still has some soil in it, but it is mostly rock fragments at this point in time. All right, so soil is composed of three main parts, and they are sand, silt, and clay. And the amount of these that are present affect how much air and water a soil can hold. Some factors that affect the composition of soil are the time that the soil has had to be created, the parent material the soil was created from, any plant or organic matter from animals that's been deposited here, the topography, so how steep the land is versus nice and gentle. This very steep land is going to have water carry these sediments down, where this kind of flatter land is going to have it go much slower. And the climate has an effect here. But the more weathering that occurs in an area, the more soil that will occur in that area. All right, next we're going to talk about the mass movements and erosion. So mass movement is the downward transportation of weathered materials. And anytime things are moving downward, it's usually because they're pulled by gravity. And erosion is different than weathering, where weathering was the breakup of rock. Erosion is the removal and the transport of materials by natural agents, things such as water and wind. So mass movements and weathering. As we get these mass movements and we get these rocks moving, we get fresh bedrock exposed all the time. This increases surface area, which speeds up the weathering process. We can get these taluses, which are these rock fragments that have been weathered along a cliff here. They have been fallen down due to gravity. They're now accumulating at the bottom. All of this up here is freshly exposed bedrock that can now be weathered. Landslides, these are movement of a mass of bedrock or loose soil or rock or all three of those down the slope of a hill, mountain, or cliff. And these tend to happen after we get these saturated soils, so things after heavy rains or snow melt. Snow itself is a very heavy thing. It has weight to it. And so increased snow means increased weight that increases the pull of gravity on that soil and may pull it down the hill. And there are four broad types of landslides. The first is a creep, which is a slow, imperceptible movement down a slope. You don't see a creep, you see the effects of a creep. So over time, from season to season, you might see fence posts, power poles, and other objects start to lean downward. This is because the soil is very slowly moving down this hill. The presence of water allows the soil to continue to creep. So the more water in an area, the faster this creep will be. A slump is when a huge or a bigger block of land is tilting and moving downhill. This happens when we get this kind of steep slope here. This whole chunk will break off and slump down so that our new kind of structure looks something like this with this hill down here, where this piece has fallen down and now the soil at the top is more supported. If this soil continues to get weathered away, it'll form that nice steep part again, and that slump will continue over and over again. All right, for earth flows, this is when we have a mass of weathered material that is saturated with water flowing downhill. It is slower than a mud flow, and the things that affect how fast this thing are flowing are the steepness of the slope, the composition of the soil, and the amount of water present. And mud flows are our fastest. They are rapid movement of water that contains a large amount of suspended clay and silt. These guys contain more water than earth flows. They can travel up to 100 kilometers per hour, which is around 62 miles per hour. And this force of water and earth together can move things like boulders and rocks and trees and houses. It's a very destructive, very powerful force. So where do we get these mud flows? Well, mud flows tend to happen in drier areas. They happen in areas that are very infrequent rainfall. They happen on areas with very steep slopes. Lahars are mudslides that happen as a volcano is kind of creating this and helping out with this liquid and hot, goopy mess that will flow down. It can happen as this magma or lava is melting a whole bunch of snow that then carries that dust and stuff down with it. So erosion has a very pronounced effect on the earthscape and the landforms that we see. So things like rivers and streams, glaciers, winds, ocean waves are all agents of erosion. They are all breaking down and moving things from one area to another. This shapes the mountains, this shapes the beaches, this shapes all of the landforms. The kind of the two important things that affect the erosion in a given region are the climate and the composition of the rock that is present. Softer rocks are going to be eroded and carried away faster than our harder ones, and areas with more climate are going to have more erosion than areas with less. Topography also plays a large role, the up and down of an area, if there's a lot of steep grades. So topography kind of brings in this balance between uplifting, which is how fast things are getting pushed upwards, and erosion, where we are slowly chunking away at these things, wearing them back down. So climate also plays a role when we have humid climates. Water is our primary agent of erosion. In these areas, the mountains aren't typically as peaked. They're more rounded, as this water is breaking that down and carrying those sediments away, eroding them to smaller bits. So some more on composition of rock. Volcanic necks. This is a volcanic neck here on the right-hand side. This is a leftover plug of igneous rock that was made of hardened magma on the inside of a volcano. The rock around this was softer and got eroded quicker, just leaving this piece left over. And in our last part of this chapter, we're going to talk about soil as a resource. Because right now, less than 25% of Earth's land can be used to grow crops. That's not a lot when we talk about that has to feed 100% of the world's population. Areas like mountains and polar regions and deserts don't have a lot of soil. Mountains are too new, they don't have enough time to have soil. Polar regions are too cold. Desert regions don't have enough water, they're too hot and too dry. Soil fertility is the ability and kind of the measurability of a soil's ability to grow plants. Things that go into a soil fertility are the proportions of mineral matter present, the water present, the amount of organic matter in the soil, the amount of humus there, determines what types of plants will grow in the soil and how well they will grow in the soil. Soil depletion happens as we have these crop plants and natural vegetation using these nutrients. When plants die, normally they decompose and their nutrients are returned back to the soil. However, when we're planting crops, we are taking their nutrients and we're taking that onion out of the ground, we're taking it to our table, we're chopping it open, and then we're eating those nutrients. So those nutrients aren't going back to the soil. When this happens, this is soil depletion, the gradual removal of these nutrients until a soil is no longer able to grow a usable crop. So there are some farming practices that we can kind of implore and use to prevent soil depletion. We can allow our fields to lie fallow or not use them for harvesting for a period of time. This returns nutrients back to the soil. We can rotate the different types of crops. Different crops use different nutrients. They put different nutrients into the soil. Things like soybeans put lots of nitrogen back into the soil. They're really good to recharge soil. We can add fertilizer to our field, which is just adding nutrients back to the field. However, the downside to this is the runoff of these fertilizers can destroy animal life and hurt plant life into any water that they run into. So there's some ups and downs there. Salinization, this is the process of mineral matter that is getting deposited from evaporated irrigation water. As this salt gets deposited, it gets saltier and saltier on the soil until eventually it creates the soil that is no longer able to sustain plant life. We need to preserve our soil. because erosion is a natural process, but as humans, we create larger surface area. We speed this up. Things like farming, construction, mining, and other activities leave soil unprotected. The wind can come and pick it up. The water can carry it away. And when this happens, what happens is the topsoil is getting eroded much quicker than it can get reformed. When we talked about resources, this makes it a non-renewable resource. So instead of, which is very expensive, pulling in new soil and dumping dump truckloads of soil onto a field, we can use some methods to conserve our soil. Things like windbreaks, things like terrace farming, and things like using contour farming or strip cropping or no-till methods are used to employed to protect this soil so we don't have to replace it. Windbreaks, or we also call them shelter belts in some regions, these are belts of trees or shrubs that are planted along the edges of fields. They are very common in the Great Plains, where there's lots of erosion due to wind. The wind has got this lot of open space that it can pick up speed and carry really big particles. By using these windbreaks, there's now less ability of that wind to get up to full speed. And this is something that we see really coming after the Dust Bowl disaster of the 1930s, where we had a drought and all of those plants dried up and the soil was just carried around, and a lot of soil depletion happened at this time. So now we take greater care in making sure that doesn't happen again. In contour farming, we're preventing water from running downhill. To prevent that, we do these rows that are contoured to the land. They're parallel to the contour of the land. And what this does is this prevents a slower path for this water to go down here. If we were to come through and just do this kind of method of planting where we go through and we till all in straight lines, this water would run very quickly down these tills. But because we don't, and we use these nice contours of the land here, we create this nice block where we're slowing down this water at each step here. Or even like this, where we're slowing it down a whole bunch. Terraces are used. We're flattening slopes here to slow the speed of runoff. So instead of just flowing freely down the hill, the water has to come to each terrace. So instead of just running down the hill like that, it has to come, drop down, go up, drop down, drop down. This slows down and increases the area that this water has to run, giving these plants more time to catch it and absorb this water. It also prevents this water from getting up to a higher speed. The higher a speed, the higher the runoff, the more soil it can carry away with it. So this terrace farming can reduce soil erosion by up to 50%, which is very significant. We like to keep our soil, so we'll take 50%. This is an old method as well. All right, in strip cropping, we have rows of crops that are alternated between those that cover the ground and those that do not. So in this picture here, there's some corn. This is kind of yellower one, and this green is alfalfa. The corn, if we had just corn here, this ground can dry out. The sun can then dry that out. Wind can come blow and pick up that soil and carry it away. This alfalfa kind of prevents that. The soil is a little bit wetter here. It keeps this moisture in these belts a little bit better to prevent this whole field from drying out. And then our last method, we use no-till farming, which when we do the plowing, the planting, and the fertilizing, and weed control all at the same time. So we're only going over the field once. Once we plant the field, it's not disturbed again. And this reduces the chance of erosion because we're not going over and tilling the soil, and we're not planting seeds in the soil, and we're not fertilizing over the soil and doing all these different steps that each time disturbs the soil and increases the chance of erosion and weathering. So that is the conclusion of chapter 12. I hope you learned a lot about soil, a lot about weathering, about what the actual definition and difference between weathering and erosion is, how we use soil as a natural resource, and how we protect it, and how we make sure that we continue to have this natural resource and are able to continue to provide food and grow a nice, happy, healthy crop. and keep that soil intact and keep that soil nutrient rich. Thank you, and see you in the next one.